Welcome back to the video lecture series for Introduction to Adaptive Programming using Scala. In this video we're going to continue working with our graph reachability algorithm that we started in the last video. Where we left off last time, we had an algorithm that, well, it worked when we went from node 0 to 3 and we were working on this graph, so 0 to 2 to 3 is a possible path, and that ran and it said true. But as soon as I changed it from 0 to 1, well, I can't get there. This ran into an infinite recursion, and then there was a stack overflow. So, stack overflow. How do we fix this? Well, the first thing we have to realize is what's the problem. It's tempting to think this only happened because we were going to a node that was unreachable. However, if I come to this graph, and what I want to do is I want to make it so that in addition to 0 pointing to 2, I want to make 2 point back to 3. I won't actually draw it in here, but we can put this in the code fairly easily. 0 points to 2, but I also want to make it so 2 points back to 0. I'll just put some positive number in there. And now I will try this where it goes to 3 again. And we run it, boom, and we get a stack overflow. Okay, so note that in this case 3 is reachable. Just adding an edge back to there does not prevent us from reaching 3, but it causes a problem for this algorithm. And if you think back to when we looked at mazes and in the last dealing with recursion, the problem that's happening here is that I can go from 0 to 2 to 0 to 2 to 0 to 2 to 0 to 2, back and forth, back and forth, back and forth. If you don't believe me, we can put some print statements up in here and just do a print line of cur. And now when I run this, indeed 0, 2, 0, 2, 0, 2, back and forth and back and forth. Okay, so what do we have to do? We have to somehow make it clear that we've been someplace before. And in the videos on mazes, we did that by leaving behind what we refer to as breadcrumbs. Okay, well, we could do that here. We would have to find some way of leaving things behind. One way of doing this is to pass in an extra argument, and we need to decide what type that extra argument should be. One option is to pass in an array of booleans, okay, and that array of booleans would have one boolean element for everything. So this would be visited as an array of boolean, and then visited, and every time that we visit something we have to turn on that bit, and we only go things, so if the graph, if it goes there, and let's actually say not visited sub I, and the graph reaches across, in that case the first thing that I'm going to do inside of here, visited sub cur equals true. Okay, so I turn it on, and this will prevent us from ever visiting the same node twice. And we could structure the logic a little bit differently, make it so it's a base case or whatnot. There are lots of ways that we could do this. So now if I run this, what do I have to do? Well, I have to pass in an array dot fill graph2 dot size of false. Okay, so I'm going to make a new array that is the same size as the dimensions on my graph, and I'll pass in everything as false. 0 to 3 will run nicely. Let me actually put the 1 back into there. It says true. Let's change that, and let's try from 0 to 1. And run that, and it says false. Okay, so it's giving us correct answers now. It didn't run into an infinite recursion. We'd have to, if we wanted to use the exists, it would require a little bit more logic. We just have to put inside of here visited. An alternative to using the array of booleans would be to pass in a set of ints, or alternately a bit set. Now, one of the big differences between passing in a set of ints and passing in the array of boolean, the array of boolean works very well for this can reach method. Because for can reach, we don't care how we got there, it's just a question of can we get there. And note that while I'm setting things in this array to be true, I'm never ever changing them back to false. And in the next algorithm that we're going to look at, that would be potentially a problem. However, for this algorithm, when we can do it this way, when we set them to true and never set them back to false, it's actually more efficient. If I passed in an immutable set of ints, well, then as I go down the recursion, I would be turning things on in this set. I would be adding elements to it. But as I pop back up, I would be going back to previous versions where the bits weren't set in them. And so it would actually wind up taking a little longer and trying more possibilities. Because the way that we've written this, much like on the mazes that we did previously, the way this algorithm works is it literally starts at wherever we tell it to start, and it tries every single path through the graph until it gets to something that will allow it to get there. I'll put back that edge, because in the next video we're going to come back, and instead of talking about reachability, we're going to look at a shortest path algorithm. I want to find out how I can get from one node to another via the shortest path possible. So we'll come back and we'll talk about that.